Hello everyone, today we will be starting with the session 4 of coordination compounds. We are previously done with the IUPAC nomenclature. Students are requested to drop down their names for attendance purpose so that we can start in a while. Okay, so let's start. Previously I gave you some question in the from IUPAC nomenclature. You have to name some of the compounds, right? So you can check your answers now. So this complex will be named as diamine chlorido nitrito N platinum. Why N? Because the coordination is from nitrogen. Then this complex will be named as pentaamine carbonato cobalt 3 chloride. This complex will be named as potassium trioxalato chromate 3. And this complex will be named as mercury tetrathiocyaneto cobaltate 3. I hope all of you have got your answers correct. All of you have got your answers correct? Were you able to name the compounds? Okay, so today we will start with theories related to coordination compounds. So, three different theories we have to study. However, there were more theories like ligand field theory and molecular orbital theory. These are studied in higher classes. We have to focus on only three theories, that is Warner's theory, valence bond theory, that is VBT, and crystal field theory. So, these three theories we have to study. Warner and VBT we will study in detail. However, we will just have an idea of crystal field theory as per your mentioned syllabus. Okay. So first is the Warner's theory. So basically an experiment was made. So it was found that in a series of compounds of cobalt 3 chloride, basically you are having a compound which is containing cobalt, chloride and ammonia, right? So it was found that AgCl could be precipitated on adding excess silver nitrate solution in cold, but some AgCl remained in the solution. So this particular stated that, for example, you are having this compound, same compound you are having, just you are changing the composition. Here you are taking 6 ammonia, here you are taking 5 ammonia, here you are taking 4 ammonia, and here also you are taking 4 ammonia, right? So first point of difference was that the colors were different. As you can see, it is of yellow color, it is of purple color, it is of green color, it is of violet color. Now this complex gave 3 mole of AgCl. It precipitated 3 mole of AgCl on adding silver nitrate solution, right? So in each of the complex solution we were adding silver nitrate, and it was found that the first one gave 3 mole of AgCl, second one gave 2 mole of AgCl, third one gave 1 mole of AgCl, and the fourth one gave 1 mole of AgCl. So why this difference was coming was stated by Warner theory. Here you can see that the one which was written as COCl3.6NH3, that means 6 ammonia ligands were there and 6 chloro ligands, 3 chloro ligands were there. So it was written as cobalt NH3 6 3 plus 3 Cl negative. That means the 3 Cl were in the ionization sphere, while the remaining ammonia ligand which were neutral were in the coordination sphere as ligands, right? So one thing you can keep in mind, that generally metal tends to form complex, with neutral ligand first, and then it forms complex with ionic ligand. Okay, so amongst ammonia and chloride, you are having ammonia as a neutral ligand. So cobalt will form bond with ammonia first, right? So here ammonia will be present as ligand and Cl negative is in the ionizing sphere. So here this complex can be written as 1:3 electrolyte. Actually what was happening, because this is in the ionization sphere and this is the ammonia was present in the complex. So when you add AgNO3 now, what will happen? That Ag and Cl will precipitate out, because on ionization this will give what? 3Cl negative separate and this complex entity as separate. So this Cl negative will combine with AgCl to give you 3 moles of AgCl. That means this particular complex will precipitate 3 mole of AgCl. Now next, in the previous compound we were having COCl3.5NH3. So here cobalt 3 always forms octahedral complex, right? So octahedral complex means 6 ligands there has to be. Now only 5 ammonia is there because metal first coordinates with neutral ligand. So only 5 ammonia are there and 1 Cl will be there. Rest of the 2 Cl will be in the ionizing sphere. So here, now on adding this complex to solution, 2 Cl negative will ionize and this will ionize as a particular entity, right? Now this 2 Cl negative will combine with AgNO3 to give you 2 moles of AgCl. So on the basis of number of chloride ion that are present in the ionizing sphere, you can find out that how many moles of AgCl will be precipitated out by a particular compound when AgNO3 is added to it. So here it becomes 1:3 electrolyte. Why 1:3 electrolyte? 1 for the complex and 3 for Cl negative. Then here it is 1:2 electrolyte. 1 for the complex, 2 for the Cl negative. 1:1 electrolyte, 1 for the complex, 1 for the Cl negative. Then 1:1 electrolyte again, 1 for the complex and 1 for Cl negative. Now here if you see that on the basis of these observations, Warner proposed a theory. What was that theory? That in the formation of complexes, there are 2 types of valencies that are exhibited by metals. One is the primary valency and the second one is the secondary valency, right? So primary valency is what? The oxidation number on the metal. The oxidation number of the metal is the primary valency. We have studied that how to find out the oxidation number of a metal atom or a metal ion in the previous class, right? So that oxidation number according to Warner's theory is the primary valency, and it can be only satisfied by anions. This is important. It can be only satisfied by anions. These are ionizable and non-directional. Basically, if you learn about ionic bond and covalent bond, ionic bond and covalent bond. So ionic bond is what? Ionizable and non-directional, while covalent bond is what? Non-ionizable and directional in nature. So primary valency is basically comprises of ionic bond that are made between the metal atom and the atoms which are, or the ions which are, or the anions which are present in the ionizing sphere, right? So in this you just have to remember that primary valency correspond to the oxidation number of the metal. Now second states that secondary valency correspond to the coordination number of the metal atom, and it is satisfied by ligand. It can be a positive ligand also, it can be a negative ligand also, and a neutral ligand also. However, the primary valency can always be satisfied by anions only, while secondary valencies can be satisfied by neutral ligand also, by anionic ligand also, by cationic ligand also, right? And these are non-ionizable and directional in nature, right? So the geometry around the metal atom or the geometry of the complex is basically decided by secondary valencies, because these valencies correspond to the coordination number. So two things you have to remember, that metal ion possesses two types of valencies. One is the primary valencies, which correspond to the oxidation number of the metal, and one is the secondary valencies, which correspond to the coordination number of the metal atom. And in a complex, metal should be able to satisfy both the primary valency also and the secondary valency also, right? So this concept you will able to understand it better when in the next slides. So here if you will see K4FeCN6 in aqueous solution, it will dissociate into the ionization sphere, and the complex, the coordination entity sphere or the coordination sphere will separate out, right? So here you can say, what is primary valency? Primary valency is oxidation number of metal atom. So what is the oxidation number here? X minus 6, because Cn is what? Minus 1. So 6Cn will be minus 6 equals to minus 4. So this becomes X equals to minus 4 plus 6, that will be equal to X equals to plus 2. So iron is in plus 2 oxidation state here, and the oxidation state of the metal is plus 2. So the primary valency will also be equal to plus 2 here. Okay. Now the second one is the secondary valency. So what will be the secondary valency here? The coordination number of iron will be what? 6, right? Because it is a monodentate ligand rather an ambidentate ligand. So it will donate only from one side, right? So coordination number will come out to be 6. So the secondary valency will come out to be 6. I hope it is clear. Are you able to find out primary valency and secondary valency now? Primary valency, you can keep in mind that it has a behavior as that of the ionic bond, right? That means, is it clear? Just a second, Sham, I am reading your question. Will you be able to find out now the primary valency and the secondary valency? Okay, good. Now, basically Warner theory was unable to account for the following stuff. That first, why only certain elements possess the property of forming coordination compounds? Why all elements cannot form coordination compounds? Why the bond in coordination compound have directional properties and they have specific geometry? That was also not explained by Warner theory. Why coordination compound have characteristic magnetic and optical properties? That was also not explained by Warner's theory. So these were the limitations, or basically you can say not the limitations, but Warner was unable to account for the following. Okay. So Warner theory, you just have to have an idea, right? It is not important, that much important from the examination point of view. The important ones are the VBT theory and the crystal field theory, right? Now answer this question. Which of the following complex produces 3 moles of silver chloride when its 1 mole is treated with excess of silver nitrate? Answer this question. Anyone with the answer? What about others except Sham? Okay. Yes. You all are correct with your answers. The option is D. Why? Because it will dissociate into CrH2O6 3 plus, and here it will be 3Cl negative plus AgNO3. Basically in aqueous solution these will ionize, right? The ionization sphere and the coordination sphere will separate out as ions in the aqueous solution, and this Ag plus and Cl negative will combine to give a precipitate of AgCl, that is 3 moles of AgCl, because we are adding here excess of silver nitrate. Okay, so all Cl negative will make AgCl as PPT. Good. Now you come on to valence bond theory. See, this is very much important from the examination point of view, right? So pay attention to this. Most of the competitive examination will focus on this concept, right? On this theory. There will be hardly a question from Warner's theory, but valence bond theory is very much important from the examination point of view. Okay. So according to this theory, see, it is almost somewhat same, not exactly the same, but somewhat same of the valence bond theory that you have learnt in the chemical bonding chapter in class 11th, right? Here also the hybridization concept will be used, right? So focus on this, that metal atom or ion under the influence of ligand, right? The metal atom or ion under the influence of ligand uses its orbitals, which orbitals? N-1d, Ns, Np or Ns, Np, Nd orbitals for hybridization. That means the atomic orbitals or the metal atom orbitals will undergo hybridization to yield a set of equivalent orbitals. That means the hybrid orbitals that will be generated will be of equal energy, same as that of the valence bond theory which we have studied in the chemical bonding chapter. Okay, now these set of equivalent orbitals, equivalent means that they will be similar in energy, they will occupy definite geometry, right? What are those geometries? Tetrahedral, octahedral, square planar, etc. So you need to remember that which type of hybridization will have which type of geometry. So if the coordination number of metal comes out to be 4 and the hybridization is sp3, that means the geometry will be tetrahedral in nature. If the coordination of metal atom comes out to be 4 and the type of hybridization comes out to be dsp2, then the geometry will be square planar. If the coordination number comes out to be 5 and the type of hybridization is sp3d, then the geometry will come out to be trigonal bipyramidal. Now, if the coordination number comes out to be 6, there are two types of possible hybridization, that is sp3d2 and d2sp3. So what is the difference between sp3d2 and d2sp3? In sp3d2 you will use the higher d orbital, while in d2sp3 you will use the previous d orbital. I'll explain it in the next slide also. So sp3d2 and the d2sp3 both will have the octahedral geometry, right? Now coordination number equals to number of empty orbitals used for hybridization. Now this is the point of basically difference between the valence bond theory that we have studied in case of covalent compounds, and here we are studying for coordination compound. See what is happening here. In the previous one, for example, let us say that we were having CH4, right? So this is a covalent compound. No coordinate bond is formed here, only covalent bond is formed, right? So carbon, we write down the hybridization, we write down the electronic configuration. What was the electronic configuration? 1s2, 2s2 and then 2p2, right? Now what happens, that one electron from 2s get excited to 2p. So this will become what? 2s1. We will not involve 1s2 in hybridization. Why? Because it is not the valence shell, right? The valence shell is only orbit number 2. So 2s1 and then this becomes 2p3. 2p3. 3. Now basically a covalent bond is made when there is equal contribution from both the atoms, right? Equal contribution of electrons from both the atoms. Now each hydrogen will give its 1 electron, right? So here what hybridization will take place? sp3 hybridization will take place, right? sp3 hybridization will take place, 1s and 3p, and hydrogen will denote its electron like this. I am drawing it with a dotted arrow, right? These are hydrogen electrons. But here there is a difference, right? Here what we considered that the number of unpaired electrons will be the hybridization number or the coordination number. But in case of coordination compound, what happens that both the electrons are donated from the ligand or the side atom, you can say, right? Both the electrons are donated from the ligand. So the orbital needs to be vacant this time. So the coordination number equals to number of empty orbitals used for hybridization. Now you don't have to count the orbitals which are having a single paired electron. Why? Because the metal atom orbital should be vacant so that the ligand can donate its 2 electron to the vacant orbital of the metal, right? This will be more clarified when we will study the basically how to draw geometry according to valence bond theory for different coordination compound. Now when the hybridization of orbitals of metal atom takes place, means the hybridized orbitals have been created which are equivalent in energy and have a definite spatial arrangement. Now the ligand orbitals overlap and donate electron pairs for bonding, right? So that will mean what? Particularly if the type of hybridization is sp3. So these will be the sp3 hybridized orbitals, which will be somewhat like this. They are arranged like this, right? If you remember the chemical bonding chapter in tetrahedral form. Now the ligand orbitals will be overlapping this. Let us say this is the ligand orbital, this will overlap with this, 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 right? So these are what? The lobes are the sp3 orbitals of metal atom, and the ligand orbitals will overlap with these sp3 hybridized orbitals. Now when we were doing the chemical bonding chapter, when we were forming covalent bond, 1 electron was donated from the side atom and 1 electron from the central atom, then a bond was made. But now here what is happening, that the metal will not donate electron, only the ligand will donate its 2 electrons. So there has to be a vacant sp3 orbital now. Okay, this sp3 orbital should not be occupied by a single electron. Both the electrons will be donated by ligand only, right? So remember the coordinate bond concept, that ligand will donate 2 electrons to metal. Okay, so metal should have its sp3 orbitals vacant and ligand will donate its 2 electron to the sp3 hybridized orbital. Okay, so yeah, now we have to study 2 types of complexes, inner orbital complexes and outer orbital complexes. Remember the hybridization in the octahedral complex, that was sp3d2 and d2sp3. So d2sp3 is known as inner orbital complex and sp3d2 is known as what? Outer orbital complex. So what is happening here? When the compounds where inner d orbitals are used, for example, you are having, let us say, 3d, 4s and 4p. These you are using for hybridization, right? Then it will be a d2sp3 complex. But if you are using 4s, 4p and let us say that you are using 4d now for hybridization, then it will be a outer orbital complex. Okay, this will be a inner orbital complex and this will be a outer orbital complex. And the low spin, high spin, we will discuss that in crystal field theory. You can ignore it for now, right? Low spin and high spin complex, or spin paired or spin free complex, these definitions are more appropriate for crystal field theory. For valence bond theory, you can remember that there are two types of complexes, that are inner orbital and outer orbital. If the inner d orbital is used, then that will be d2sp3, and if the outer d orbital is used, then that will be sp3d2. okay. Now, strength of ligands. Particularly, what happens here is that VBT only defines that there are two types of ligand, right? One is the strong field ligand and one is the weak field ligand. It has not given the idea that how can you classify that a particular ligand is strong field or a weak field ligand, but it has just mentioned that these ligands will be strong field ligands and these ligands will be weak field ligands. Okay, so when the ligands are arranged in a series in the order of increasing field strength, that is known as spectrochemical series, right? So this is from CFT, crystal field theory, that we will discuss in the next session most probably, right? So here we are having a spectrochemical series which will decide that a particular ligand is strong or not, strong field ligand or a weak field ligand or not, right? Now, what is the purpose of classifying ligands as strong field ligands or weak field ligand? So, strong field ligand are able to pair up electrons. Strong field ligands have the ability to pair up electrons, while weak field ligand do not have the capability to pair up electrons. They do not pair up electrons. For the time being, you can understand just this much, that strong field ligand will pair up electrons while the weak field ligand will not pair up electron, right? The reason we will discuss in the crystal field theory. So this series you have to remember it by heart. I negative, Br negative, SCN negative, chloride, sulfide, fluoride, hydroxide, oxalate, water, NCS negative, EDTA, NH3. Till this, there are weak field ligands. These are weak field ligands. While cyanide and carbon monoxide, or you basically name it as carbonyl in coordination chemistry. So, carbon monoxide or carbonyl to be more appropriate, and cyanide Cn minus are the strong field ligands, right? So till from I minus till ammonia, you remember that these are weak field ligand, right? Ethylene diamines, cyanide and carbonyl are strong field ligands. Now there is speciality for some ligands. See, H2O, if you are having, it behaves as, rather it is a weak field ligand only, but it behaves as strong field ligand with cobalt 3+. This you should write down, that with cobalt 3+, H2O behaves as strong field ligand. That means it has the ability to pair electrons. Just write it down in your notebook somewhere, because these are some special cases. Okay, so cobalt 3+ with water behaves as a strong field ligand. Otherwise, it will behave as a weak field ligand. Okay, and Cn minus, CO and ethylene diamine will always behave as a strong field ligand. I minus, Br minus till ammonia will behave as a weak field ligand. Ammonia also, there are special cases, we will discuss them in between, but for the time being you can write down that water with cobalt 3+ act as a strong field ligand, and with other metal ions it will act as a weak field ligand. Okay, this series you have to remember it, remember by heart. Okay, it can be asked directly in the examination also, that which one is a weak field ligand or which one is a strong field ligand. So questions like this can also be asked. Now, valence bond theory does not explain the aspect of strength of ligands clearly. It has just defined that these will be strong field ligands, or it has just defined that these will be weak field ligands. But why it is acting as a weak field ligand, why it is acting as a strong field ligand, why strong field ligands are able to pair up electrons and why weak field ligands are not able to pair up electrons, this was not explained by valence bond theory. So this is one limitation of valence bond theory. Now we will do some examples. Focus on the examples, right? Once you understand the concept, you will be able to find out the hybridization, geometry and other things for any complex. Okay, I'll explain you some examples and then you can practice on your own also. See, first we will do with 6 ligands. That means coordination number will be 6. If there are unidentate ligands, that means monodentate ligand. So the coordination number will be 6, right? So the first complex that we will be doing is cobalt 3 plus NH3 6, right? Write down that in octahedral complexes, write down for ammonia, in octahedral complexes, if the metal atom has 3 plus oxidation state, then ammonia will behave as a strong field ligand. Water and ammonia are having special cases, so just only 2 cases you need to remember, that cobalt 3 plus with water, it will behave as a strong field ligand, water will behave as a strong field ligand, otherwise it will behave as a weak field ligand. And in octahedral complexes, if the metal is present in +3 oxidation state, then ammonia will behave as a strong field ligand. While in octahedral complexes, if the metal is in +2 oxidation state, then ammonia will behave as a weak field ligand. Write it down in your notebook. This is very much important from the examination point of view, that in octahedral complexes, if the metal atom is having +3 oxidation state, then ammonia will behave as a strong field ligand. But if it is having +2 oxidation state, then it will behave as a weak field ligand. And water with cobalt 3 plus will always behave as a strong field ligand, otherwise it will behave as a weak field ligand. Okay. Now let us study here. So cobalt is in +3 oxidation state. That means what? CO3 plus. And we know in octahedral complex, if the metal atom is having +3 oxidation state, then ammonia will act as a strong field ligand. And what is the meaning of strong field ligand? That it is able to pair electrons, right? This much we have inferred. Now what we have to do, see, first you write down cobalt. What is cobalt? The electronic configuration of cobalt, 4s2 3d7, right? And what will be the electronic configuration for cobalt 3 plus? It will be 3d6, okay? So 4s and 4p are vacant and we have drawn 3d6. Now if we are having octahedral entity, that means the possible hybridizations are what? sp3d2 or d2sp3. Either I use the 3d orbitals or I use the 4d orbital. Now this will depend upon the type of ligand that you are using. So here it is strong field ligand, that means it has the ability to pair electrons. Now I want 2 orbitals of d vacant for the d2sp3 hybridization, right? Why we want it as vacant? Because in these orbitals the ammonia will donate electron. Right, 2 electrons will be donated by ammonia, 2 electrons will be 2 electrons here, 2 electrons here, 2 electrons here and 2 electrons here. So we need vacant orbitals. Now because ammonia is acting as a strong field ligand, it has the ability to pair up electrons. What it will do, that this electron it will pair up with this and this electron it will pair up with this, and these two will be the vacant positions now, right? Now these orbitals combine to form hybrid orbitals d2sp3, right? And in these orbitals, now what happens, that these are the d2sp3 orbitals and in each orbital ammonia will donate its electron. So 2 electron here it will donate, 2 electron here it will donate, 2 electron here, 2 electron here, 2 electron here, 2 electron here. 6 ammonia are there. So 1, 2, 3, 4, 5, 6. Is it clear? So because it is using 3D, that is the inner orbital, therefore it is known as inner orbital complex. D2sp3 will be known as inner orbital complex. Is it clear with you all? Are you able to understand, or should I explain it again? This is very important from the examination point of view. Let me know in the comment section box. Okay, good. So see, now we can identify that the complex is diamagnetic or paramagnetic based upon the number of unpaired electrons. So here you can see that 2 electrons are being filled here. Here also the electrons are paired, and here also the electrons are paired. So this complex is diamagnetic complex. Okay, because all electrons are paired, so it will be diamagnetic complex. Now the next complex, COF6 3-. First thing, you need to find out the oxidation state of cobalt. So this will be X minus 6 equals to minus 3. So this will be X equals to minus 3 plus 6. X will give you what? Plus 3. That means cobalt is present in plus 3 oxidation state. Now you identify fluorine is what? A weak field ligand. So fluorine is what? A weak field ligand. That means it will not be able to pair up electrons. Right? This much is clear. Now, next is that we are having 6 fluorine. That means what? That coordination number is 6. So, two types of hybridizations are possible. Either D2sp3 is possible, or either sp3d2 is possible. Right? Now you begin. Cobalt is what 4s to 3d7. So cobalt 3 plus will be what? 3d6. So this is 3d6. We are not having the d orbitals vacant here, and as fluorine is a weak field ligand, so it will not be able to pair up electrons now. It does not have the option to make these two 3d orbitals unfilled or basically vacant by pairing up the electrons which are present in the d orbital, because it is a weak field ligand. So the option that is left with us is that we will use 4s, 4p and 4d orbital. So these orbitals will give you what hybridization? sp3d2 hybridization. Why? Because we are using 4d orbital now. So it is a outer orbital complex. Right? Now you fill electrons in the sp3d2. Right? 6 electrons will be filled and 3d will remain as such. 3d will remain as such because pairing of electron cannot be take place because fluorine is a weak field ligand. Right? Now you tell that the complex is paramagnetic or diamagnetic. So here it is diamagnetic. You can see that the fluoride ligands has basically donated 2 electrons in each orbital, right? So this will be, this part is fully paired electrons, is having fully paired electrons. But here if you see in 3D, what is happening, that 1, 2, 3, 4 unpaired electrons are there. So because of the 4 unpaired electrons, this complex will be paramagnetic. Okay, I hope this is clear. The outer orbital complex and the inner orbital complex. Now, we will learn about coordination number 4. Right? So coordination number 4, two types of geometries are formed. That is sp3 hybridization will give you tetrahedral geometry, and dsp2 hybridization will give you square planar geometry. Okay, now we will consider that in which cases dsp2 will be formed and in which cases sp3 will be formed, right? This will also decide that the 4 ligands will be arranged in a square planar geometry or they will be arranged in a tetrahedral geometry, right? And we will also classify them as inner orbital complexes if the d orbital that is used is the inner one, or the outer orbital complexes. Now here, first is the inner orbital complex, that is nickel Cn4 2 minus, right? For the time being, you forget that it has been written that it is an inner orbital complex. Just forget that, right? We need to find out by ourselves that whether it is an inner orbital complex, whether it is an outer orbital complex, or which type of geometry it is having, right? So this complex name is just given. First step is what? Finding out the oxidation state. First you find out the oxidation state. X minus 4 equals to minus 2. So this will give you what? X equals to minus 2 plus 4. That will give you what? X equals to plus 2. So nickel is what? Plus 2. Now nickel electronic configuration is what? 4s2 3d8. Plus 2 will give you 3d8. 4s will be vacant and 4p is vacant only, right? Now we have to decide the ligand. Now cyanide is a ligand, it is a strong field ligand, so it will be able to pair up electrons. Now the possible hybridization in coordination number 4 is what? Either dsp2 we make or sp3 we make, right? Now because cyanide is a strong field ligand, it will pair up the electrons because we need only one d orbital vacant. So here it will pair up the electron. Now it has paired up the electron. Now this d orbital is vacant, this s is vacant and 2p is vacant. So these will hybridize to form dsp2 hybridization. And because we are having dsp2 hybridization, therefore it will be a square planar geometry. Square planar geometry. So the structure will be somewhat like this. Nickel, draw coordinate bond Cn, then Cn, a square planar geometry you have to make, Cn and then Cn. Okay, so as 2 electrons are donated, so this one is paired and this one is also paired. The d orbital is also paired, right? So overall it is a diamagnetic complex. Overall it is a diamagnetic complex, and also you can term it as inner orbital complex because we are having the we are using the inner d orbital. However, the term that is inner orbital complex or the outer orbital complex, it is more frequently used for only 6 ligands in which we are having coordination number equals to 6. That means in octahedral geometry it is more frequently used, right? However, because we are using here the inner d orbital, you can term it also inner orbital complex. Now next is the outer orbital complex, that is the COCl4 minus. Now here cobalt is in +3 oxidation state. Okay. Cl is a weak field ligand. Okay. Coordination number equals to 4. Either tetrahedral geometry or square planar geometry. For tetrahedral geometry we should have sp3 and for square planar we should have what? dsp2, right? Now because it is a weak field ligand, it will not be able to pair up electron. Now cobalt is what? 4s2 3d7. So cobalt 3 plus will be what? 3d6. So this is 3d6 we have drawn, right? Now because it is a weak field ligand, it will not be able to pair up electrons. So we are only left with the option to use sp3 orbitals. So this will give you sp3 hybridized orbital in which the Cl will donate 2 electrons in each orbital. Because of the unpaired electrons that are present, how many unpaired electrons are present? 1, 2, 3, 4. So because of these 4 unpaired electrons, this complex is paramagnetic in nature. This complex will be paramagnetic in nature. Now next is nickel Cl4 2 minus. So nickel is in +2 oxidation state, right? So if nickel is in +2 oxidation state, nickel is what? 4s2 3d8, right? So nickel 2 plus will be what? 3d8. So 3d8 we have made already 1, 2, 3, 4, 5, 6, 7, 8. Because Cl is what? A weak field ligand, that means it will not be able to pair up electrons. So we are left with only hybridization, that is sp3 hybridization. Because of two unpaired electrons, it will be paramagnetic in nature. Okay, and the hybridization will be sp3, that means it will have a tetrahedral geometry like this. Nickel, Cl, Cl, Cl and then Cl. I hope it is clear. Next. Now this is important. We are having tetracarbonyl complex of nickel. So here the oxidation state of nickel is 0. So it will be what? 4s2 3d8. 4s2 3d8. Now this one is very important. See, we are having 4s2 3d8. So basically the s orbital is not vacant now, right? So what we do, we make it as, because the energy difference between 3d and 4s is not appreciable, that means the distance, the energy difference is not very high. So we promote the two electrons back into the 3d. So this will be what? 3d10, 4s0. This is a very important case of nickel, that in oxidation state 0, it will become from 4s to 3d8 to 3d10, right? Now we are having what? 3 orbitals vacant, 1s and 3p, so it will follow sp3 hybridization and tetrahedral geometry, because all electrons are paired, so therefore it is a diamagnetic complex. This is a very important complex. Again, I am repeating that from 4s to 3d8, it becomes 3d10, 4s0. Now, this the 4s and the 3p will be getting hybridized to form sp3 hybridized orbital, right? And the overlap with ligands will take place, in which the ligand will donate 2 electrons for bonding. Now, next. Now, this is very important. Case of ammonia, when particularly you have to use ammonia as a strong field ligand, or when it should be used as a weak field ligand, right? So, the behavior of ammonia will depend upon the central atom, coordination number and the oxidation state. Remember, if the central atom, if the metal atom is of 3D series, that means it belongs to the 3D series, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, right? So, if this metal atom belongs to the 3D series and coordination number is 6 and the metal atom is having +2 oxidation state, then ammonia behaves as a weak field ligand, as I have explained before. And if the metal atom is in +3 oxidation state, that means what? If the central atom is of 3D series, the metal is of octahedral geometry, the coordination number is 6, right? And the metal is in +3 oxidation state, then it behaves as a strong field ligand, right? And if the coordination number is 4, then it behaves as a weak field ligand, no matter what the oxidation state of the metal is. While if the metal is of 4D and 5D series, it will behave as a strong field ligand in any condition. Okay, I'll once again repeat. I'll give you this in the form of a chart. We are having 3D, 4D and 5D. So for 4D and 5D, ammonia will always behave as a strong field ligand if the metal atom is from 4D or 5D. Now 3D will have two cases. Either octahedral geometry is there or tetrahedral geometry is there. If the coordination number is 4, that means tetrahedral geometry, it will always behave as a weak field ligand. While octahedral will have two cases. What are the two cases? If the oxidation state is +2, then it will behave as a weak field ligand, and if the oxidation state is +3, then it will behave as a strong field ligand. This you should know about ammonia. Ammonia is a special case, and one special case I have already told you, that is water with cobalt 3 plus will behave as a strong field ligand, and in rest of the cases it behaves as a weak field ligand. Is this clear to all? Will you be able to draw these structures now? Will you be able to draw these structures now? Predict the geometry, predict the hybridization, predict whether the complex is paramagnetic or diamagnetic. Some more examples we will do. Nickel 2 plus again, so this will be what? 4s2, 3d8 it is having. Nickel 2 plus will have what? 2 electrons will go away. This will become what? 3d8. Now because ammonia is in octahedral complex, basically nickel is having an octahedral complex, coordination number is 6 and +2 oxidation state, so nickel will behave as a weak field ligand now, as we have discussed in the previous slide, right? So it will not pair up the electrons, we will use the outer d orbital. So the hybridization will come out to be sp3d2. Okay, and it will be paramagnetic because of the presence of 2 unpaired electrons. Next is copper NH3 2 plus. Now this is a very important example, right? This you need to focus upon. This is an exception, you can treat it as an exception. So copper is in +2 oxidation state. So what is the electronic configuration of copper? 3d9 4s1. Okay, copper 2 plus will be what? 3d8. I think, yeah. Copper is what? 4s1. I think it is wrongly drawn. Just a second. 4s1 3d10 it is. Right? 2 electrons will be here also. Sorry, the 2 electrons are missing here. Yeah. So 4s1 3d10 and 2 plus it will be what? Basically 1 electron from here will go, 1 electron from here will go. So it will become what? 3d9. Right? Now because 4, the coordination number is 4. 4 ammonia are there. So coordination number is 4 as it is a monodentate ligand. So if the coordination number is coming out to be 4, only 2 types of hybridization is possible. Either the sp3 hybridization is possible or the dsp2 hybridization is possible. Okay, now for dsp2 hybridization to happen, what should be done? That this electron should not be there, right? This electron should be vacant somehow, right? So first it was predicted that it was having sp3 hybridization, right? It was predicted that it was having sp3 hybridization. If it was having, let us say, sp3 hybridization, right? So this means that the 1s here, just a second, it is getting messy here. Yeah, 1s here and 3p will be used, right? But sp3 hybridization was not found in this case. This is very important example. Although we should predict, because ammonia is a weak field ligand, so pairing up will not take place, right? And also there is no possibility of pairing also, right? You can see here that there is no unpaired electron other than this electron, and we want only one d orbital vacant. And because ammonia is a weak field ligand, so we expect that ammonia does not do pairing of electrons, so the hybridization should come out to be sp3. But this complex is not found in tetrahedral geometry. This is an exception. This is not found in tetrahedral geometry. Rather, it is found in square planar geometry. Square planar geometry means what? That it should have a dsp2 hybridization. But here the d orbital is not vacant. It is having one unpaired electron. This should be vacant for dsp2 hybridization. So what happens here is that the promotion of electron takes place from this d orbital to 4p orbital. This is a very important example. I am again repeating, we expect that this complex should have a sp3 hybridization, but this complex is having a dsp2 hybridization. Okay. So what is happening here? That the electron is promoted from 3d to 4p. Right. Now the dsp2 hybridization takes place. And because of the presence of this one unpaired electron, we are having a magnetic moment of 1.73 Bohr magneton. Right? As we have done in D block, I guess in D block chapter we have done that the number of unpaired electrons can give you the magnetic moment as n into n plus 2. I hope you remember. I have given you the trick also that one unpaired electron will give you 1.7, 2 will give you 2.8, 3 will give you 3.9, 4 will give you 4.9 and so on, right? So here it is one unpaired electron, so a magnetic moment of 1.73 Bohr magneton is also observed. So you have to remember this special case that one electron is promoted to the 4p and now the dsp2 hybridization takes place, okay? So this was all about valence bond theory. I'll give you some questions. You practice those. Okay. You can write down the complexes or you can take the screenshot. Yeah. Take a screenshot of these complexes. The first complex is manganese CN6 3-. First homework is this. Second is this MnCl6 3-. Third one is FeCN6 3-. Fourth one is FeF6 3-. Fifth one is cobalt C2O4 3-. Then cobalt F6 3-. Yeah. So these are your homework. Okay. We will discuss the answers of these with explanation in the next class. Okay, I'll explain you once again. See, what is happening here? Copper Ni4 2+, because here we are having the coordination number 4, right? So, two types of geometries are possible. What are the two types of geometries that are possible? One is the tetrahedral geometry and one is the square planar geometry, right? Because ammonia is acting as a weak ligand in coordination number 4, so we expect that pairing of electron does not take place. Here also, if you will see that we should observe or we should predict that sp3 hybridization should be there, right? Because you can see that there is no unpaired electron to pair this electron, right? The rest of them are already paired. So we expect that this remains as such and sp3 hybridization should be followed, right? But this is not observed. Rather, we observe a dsp2 geometry. A dsp2 hybridization or a square planar geometry is observed. So explanation for that was made that this electron must have been promoted to p orbital, the 4p orbital, right? Now this electron will be promoted to 4p orbital, so this will become vacant. 1d, 1s and 2p are becoming vacant. Now the dsp2 hybridization can take place and now this complex will have a square planar geometry. And because of this one unpaired electron, rest all of the electrons are paired, right? Because of this one unpaired electron, we are observing a magnetic moment of 1.73 Bohr magneton. Is it clear now? Yeah, when the electron is shifted to the p orbital, now 1d is vacant, 1s is vacant and 2p orbitals are vacant. So dsp2 hybridization will take place, right? And now the electrons will be filled in the dsp2 hybridized orbitals. And because of this one unpaired electron, we are having a magnetic moment of 1.73 Bohr magneton. Is it clear now? This is just an exception to a regular rule. According to the theory, we should have had a tetrahedral geometry or sp3 hybridization, but experimentally it was found that it was having dsp2 hybridization or square planar geometry. See, I'll draw it for you. 1, 2, 3, 4. So 4 orbitals will combine to give you 4 dsp2 hybridized orbitals. So these are the 4 dsp2 hybridized orbitals, right? One here is incorrectly drawn. One here is incorrectly drawn. One electron will be there in the 4p rather. Right. So this one will be the 4p. This one will be the 3d. This one is for 3d and these are for dsp2 hybridized orbitals. Is it clear now? Okay. Okay, so practice the questions and the answers we will be discussing in the next class. So that's all for today. Happy learning to all.